Hello, welcome to Sudokult episode 8. I'm back with my standard co-host, Philip Newman. Welcome back, Philip. I hope you are feeling much better.
I am.
That's great.
That's mostly recovered.
So today we are going to start by, of course, going over the challenge puzzle from Shai from episode 7. But the main episode today is going to be about uniqueness and deadly patterns, and also a little bit of theory on how did the search for 17 given Sudokus work. And it is an ongoing search, but almost all of them have been found. And how did that work? Was it just straight brute force? Spoilers, no, it was not. There's some very clever stuff going on, and it can actually help you with understanding how Classic Sudoku works in terms of uniqueness techniques and even setting them and understanding a little bit about why you need to put givens in certain places in order to have a unique solution. So I know a little bit about this topic, but I'm going to be learning along with you guys because Philip hasn't given me any primers this time. So I will be as impressed as hopefully the rest of you are with Philip's knowledge on the topic. And yes, this is icky uniqueness that we talked about before. So
uniqueness.
You don't have to use this in your solving. Every puzzle should be solvable without uniqueness, but uniqueness can make it easier if you know you are guaranteed that there's only one solution to Sudoku, and hopefully every Sudoku you do actually does have that property. Otherwise, you're not going to be able to solve it anyway with regular techniques. So I do not recommend using uniqueness techniques when you're setting a puzzle, though, because your puzzle is not unique while you're setting it, and they are not valid. So, all of that said, go ahead, Philip, and get started.
All right. So, this is Shai's Roman candle version 2 that was posed last time. This is a very hard puzzle. The firework techniques are kind of new to everybody. Shai has just been running with them and doing all sorts of crazy things. So I actually forgot to look at this until this morning. But I was able to figure out what was going on. So let's start with the firework itself. I've got some things marked in the grid. So obviously we're going to be looking at those cells. But the first thing to identify is where the firework is. And if you're looking for a digit that appears a lot, that's restricting places in the grid, you're looking in the wrong place, because it's this one right here doing all the work by itself. In row and column 5. This one eliminates one from here and from here. And so in column 5, one can either appear in one of those cells in box 5 or up here in row 1. And similarly for row 5, it can appear here or here. So what that tells us is either there's a 1 here or there's a 1 in one of these cells. Either there's a 1 here or there's a 1 in one of these cells. So if there were no 1 in either of these cells, it would have to appear in that cell in box 5. So what we can say from the firework is that one of these cells is purple for fireworks, I guess. Fireworks can be color.
Any color.
One of these cells has to contain a 1. Could be more than one. Both of these could contain and the one in box 5 could be here. But at least one of those contains it. Okay. It's not obvious how to use that, just on its own. So this is combined with something that is called a multi-sector hidden set. It's kind of the inverse of the multi-sector locked set that we talked about. And basically the way this works is rather than looking at cells and figuring out what the most of particular digits can go in those cells is, we're looking at digits and figuring out which cells they have to go. So in row 1, I have these 2 cells pencil marked. But the reason they're pencil marked is these given 3s are ruling out 3 from these those cells. So the 3 in row 1 has to appear in these 2 cells. I'll mark that orange. In row 9, the 8 is the same way. It's pretty symmetrical puzzle. 8 has to appear in those cells. In column 1, the 6 has to appear in the cells. I'll do those. Same over here for 7. 7 is there.
Mm-hmm.
All right. Now, if you had done basics on this first, because I haven't in this example, you might notice that 4 has to be in one of those cells in row 5. So what that means is it's not in either of those cells.
Right.
And that means that in this column, it's in these 3 cells.
Column is green.
And similarly, in this column, 9 has to appear. Wrong. Sure that happened. 9 has to appear in one of those cells, so it's not in these 2 cells. So it must be these cells. All right, that's pretty complicated. That's tricky to spot.
No kidding.
No kidding. It's as well as you can. It's telegraphed that you should be looking at some of these cells, the way these givens are placed.
Mm-hmm. Looking at those rows and columns.
Yeah. If you found this without getting any sort of hint, very well done. It's hard to spot. What does it tell us, though? It tells us that within these 7 cells, we know we have a 3 in row 1. We know we have a 9 in row 5. We know we have an 8. We have a 6 in column 1. We have a 4 in column 5. We have a 7 in column 9. And we have a 1 in firework in those 3 cells. That's 7 different digits that need to be in 7 cells. So what can we conclude?
That those must be in those cells. So it's like a hidden triple or something where you remove the other candidates from those cells.
It's a remote hidden subtuple. Basically. So 2 and 5 can't go. That's what I just removed. 2 and 5 can't go in those corner cells because they're not part of that subtuple. There is one more deduction that you can make. I don't remember if this is actually needed to solve the puzzle. For example, removing the 2 down here leaves us with a 2 there. And things like that will get you going. The other deduction that you can make is that none of these cells can be 1. And that's a little trickier to see. But let's think about what would happen if this were 1. In row 5, the 1 would have to be here, right?
Yep.
But also in column 5, it would have to be here. And now there are 2 1s in our firework, which for the firework is not a problem. But since we needed 7 digits for 7 cells, we can't have a duplicate 1. So that's the other elimination.
That's cool, yeah. Basically, the firework is saying at least 1 is in purple, but now because of the hidden, what did you call it?
Hidden subtuple, or it's a multi-sector hidden set.
Yeah, because of that multi-sector hidden set, we can't have more than 1 in the purple either.
Right. So that's how to solve Roman candle.
Does that not place a 1 in the center cell?
It does not. It looks like it might, but you could have a 1 here. and a 1 here. And
Nice.
that would cover column row 5.
Okay,
That's
so
what
yeah.
I was thinking when I was first looking at it. Wait, that's not the cells that Shai referenced.
Okay.
Yeah, so that's how you solve it. It is a very cool pattern and a very cool construction. Getting all that to work.
So I assume we don't have to go over it, but I assume that there's a way to use set to view kind of the same thing.
There might be. I haven't really explored this. So, like I was saying, a multi-sector hidden set is sort of the opposite of multi-sector locked set. In that here we're saying there has to be a 3 in these cells. With a multi-sector locked set, we're saying we can place, say, a 3 and a 5 in some of these cells, but there's only 2 digits. So we have 2 digits that can fit in the row in those cells. And we end up with sort of a counting argument where we can have at most 20 digits in these cells, and we have 20 cells. So they have to appear that way in some sense. And for basic MSLS, that's just row and column based, you can find a set very easily that corresponds to it. I haven't looked at correspondences between sector hidden sets and set. I'm sure there is something, but it may look a little different. I don't know. The obvious thing to try here would be to look at these and to look at these.
Right.
And you may be able to get there with that. I don't know, though. Probably have to use some additional logic. So, okay. So, moving on. So, you mentioned we're going to talk about how 17 clue puzzles are found in Classic Sudoku.
Yeah.
Additionally, we're going to talk about why 17 is the this has actually been proven, and this is one of the most common questions that you'll see when people are asking about Sudoku. They see their first few Sudoku puzzles, and the immediate thing to ask is, well, how many givens do I actually need?
Right.
This puzzle has 26. Do I need 26? Can I have a puzzle with 20? Can I have a puzzle with... You can have a puzzle with 17. And these were found fairly early. I don't know how to pronounce Nikolai or the Japanese puzzle company. They had found some puzzles with only 17, but nobody was able to find a 16. And for a long time, people were generating 17 clue puzzles using the techniques that we still use for searching for hard puzzles. Of course, you and I have been involved in looking for minimal anti-knight puzzles and Sudoku X puzzles, and so along with a few other people, Ryakusha predominantly, but other people have been involved in that.
He's the champion of searching for this stuff.
Yeah. So yeah, we got a mention recently on Cracking the Cryptic. You were able to conclusively prove that there are exactly 4 ways to 8 given anti-knight.
Yeah, and the way I did that is going to be very different from the 17 given proof.
Yeah, and maybe we'll talk about that at some point, because it's a very cool method.
Mm-hmm.
So that was how this was studied for a long time. People would take puzzles that had 17 givens, and they would try to modify them. They would add some givens and remove some givens, see if they could find other 17s that were different. One thing we should talk about first is, what do I mean by different?
Right.
So, let's say I have a puzzle that looks like this, and it has some other stuff here, whatever it is. That's one puzzle. This is also a puzzle. And from a very literal point of view, that is a different puzzle.
Right. The two's there and the one's there.
It has givens in different places. We talk about something called essentially different. And what this is really talking about is transformations of a puzzle that preserve certain properties of the puzzle. So when I swap row 1 and row 2, what does that change about the puzzle? Well, it changes what givens are in row 1 and 2. It swaps them. But it doesn't really change anything else about the puzzle. If I were to solve that puzzle, the first puzzle, if I were to solve this, I would have a logical path for solving the puzzle. If I then went to solve the second version of the puzzle, I would have exactly the same logical path, except everywhere I was using row 1, I would be using row 2 instead. It doesn't change anything about the path. Another thing it doesn't change is whatever the solution to the first puzzle is, this puzzle has exactly the same solution, except with rows 1 and 2 swapped.
Right.
Everything else is identical. So this is just one example of a transformation you can have. You can swap rows within a single band. Now you can't swap this row and this row. This would be a different puzzle.
Right.
Now the 1 and the 2 are in different bands. And the logic will be different. You can also swap columns within a band, or within a stack.
Yep.
So stack is a set of 3 boxes vertical. A band is a set of 3 boxes horizontal. You can swap columns within a stack. You can swap rows within a band. You can swap the bands or the columns. The bands are the stacks entirely. So I can move this 1 over here and move this 2 over here. That's fine. You can rotate. So if you rotate by 90 degrees, and the 1 is up here and the 2 is up here, that's the same puzzle.
Yep.
Just rotate. You can reflect it. And of course, the last thing to do is you can permute the digits. Right. Change all the 1s to 5s and all the 2s to 6s.
Yeah, because at least in Classic Sudoku, unless you introduce certain variants, the actual value of the number doesn't matter. You could use. I think I've even seen like versions of Sudoku that use emojis instead of numbers, or you could use letters or pictures or whatever you want. It's just different text, representations of 9 distinct things.
I think I've read that for children's Sudokus, so like 4x4, 6x6 Sudokus that they might have in the classroom, they'll use colors instead of. So yeah, these are all transformations for Classic Sudoku. As you add variants, some of those transformations aren't going to work anymore.
Right.
So if I add a diagonal restriction, if I say these have to be different, I can't just swap rows 1 and 2 now, because that's going to make these cells on the back. There are still some transformations you can make, but it's more limited.
Interestingly, in that case, swapping row 1 and 2 actually does work, so that was a bad example, but there are a lot of row swaps that don't work with
not just 1 and 2 though. You have to swap 1 and 2 and columns 1 and 2.
Right. Yeah, that's true.
Yeah. With Sudoku X, you have to do pairs just because of the way the diagonals work.
And then you introduce something like anti-night, and suddenly it's just you can rotate and reflect, and that's it.
Yeah, you can't swap anything. Because row 1 only sees these cells by anti-night, but this sees more cells by anti-night.
Right. They start peeking into opposing bands and stacks, and now even the order of the bands and stacks matters.
Yeah. So those are different transformations you can make. So you know the answer to this. How many different solution grids are there in a Classic Sudoku?
Memorized
off the top of your head?
No, I always go to the Mathematics of Wikipedia article and I copy paste from there.
Sudoku, yeah.
It's on the order of 10 to the 20-ish. I don't know if it's 26 or 22.
I guess 21st.
21.
So,
okay.
Yeah, it's north of 6 sextillion different solution grids. But that's without considering these transformations. So one thing you can immediately do, you don't want to look through all of the 6 sextillion solution grids looking for puzzles with only 16 givens or 7. So the way you reduce that is you take all these symmetries of the grid into account, and you look at representatives of each of the different equivalence classes. So another way of saying that is, if I have 2 solution grids and there is some transformation between the two, swapping rows, swapping columns, swapping bands, swapping stacks, rotating, reflecting, remeaning digits, then they're in the same equivalence class. So whatever I'm doing to those puzzles, whether it's solving them or searching on them or whatever, I only have to care about one of them. So you pick one. And it's not as simple as taking that 6 sextillion number and dividing it by whatever. Because some puzzles, if you do a few transformations, you end up back at the same puzzle. It's called an automorphic puzzle.
Like if you start at the North Pole and you go south 100 kilometers and then west 100 kilometers
Right.
and then north 100 kilometers. If you start at the North Pole, you end up back where you started, but anywhere else on Earth, you don't. So
there are a few other places you can. A little circle around the poles. But yeah, that's the basic idea. So I'm going to go ahead and show this. We'll come back to this. This is the so-called most canonical Sudoku grid.
I think someone pointed. I think it was Sam Kappelman Lines who said to me, "This is the grid that if someone were to just try to plunk down an easy, just plunk down numbers and get a valid solution, this is what they'd come up with."
Right. This is basically, I'm going to put the smallest number that I can as I go left to right and top to bottom, and it still be valid. You could try and put a 1 there, but you're going to break your Sudoku. So in addition to being the smallest in terms of, if I wrote this as a string, it would be the first alphabetical. It also has the most automorphisms. I think there's 648 ways to change this and end up back where you started. So just a little bit of trivia. The vast majority of essentially different Sudokus don't have any automorphisms. So however you change them, you will change the solution, but you'll stay within the same equivalence class. But you have to account for the ones that have these automorphisms.
We should point out that normally rotations and reflections are a multiplier of 8. But because we also allow swapping rows and columns and boxes and things like that, those can have the same effect as a lot of the rotations and reflections. Right. So it ends up a multiplier of 2 instead. You just have to pick one rotation.
One rotation. Yeah. If you think about reflecting this from here to here, I can accomplish the same thing by switching this band, and then switching these with each other.
Right.
And these. It accomplishes the same thing as anyway. Just a little bit of trivia. So, in actuality, there are like 5.4, I think, billion, essentially different Sudoku solutions. That's still a big number, but that's something you can work with. So that's a starting point. Okay, so we have that many solution grids. How do we go about showing that none of them have 16 given puzzles? And one thing you could try is just removing digits until you arrive at a unique Sudoku and can't remove anymore. But if you try and do that in every possible way, you'll be there for a very long time.
Yes.
Because you have 81 cells to remove from. That's just too many possibilities. So we have to be clever. How can we be clever about it? So this is where we relate to uniqueness. I'm going to show this grid. I've got some different things marked in different colors. If you can't tell the colors apart, I'm going to highlight as I talk about them. So, what I have highlighted here are called unavoidable sets. So let's just talk about the simplest one over here. There's a 3-4 in row 3. There's a 4-3 in row 8. Why do I care? Why do I care that I have that pattern? Well, if I were to remove, it's not a set. I'll come back to the same box. So I have a solution with that. If I were to remove these digits and just leave it as, I know there's a 3 and a 4 there, but I don't know what order they're in. And that would have to be the case. That would have to be the case here, because everything else is in. I don't have a unique solution anymore. So we already saw one solution where it was like this, but I can just swap those.
Yep.
And that is now a solution to the Sudoku. It's a different solution group. These wouldn't even be in the same equivalence class. But there is a solution that has this pattern, and everything else is the same. So that's a problem. What does that tell us, though? Well, it tells us that if I have a puzzle with this solution, no matter where the givens are in that puzzle, at least one of them has to be in one of those yellow cells. So otherwise I have no way of telling which way around the 3 and 4 are. So that's why it's called an unavoidable set. You can't avoid putting a given in that set of 4 cells and still have a solution.
Yeah. And I'd like to point out, because I've made this mistake before, much, much earlier when I first started, when I first learned about unique rectangles, I started seeing them everywhere, but I didn't quite understand the restrictions on them for when they are actually, this is called a unique rectangle, when they actually are a unique rectangle and when they aren't and they're fine. So for example, I would have, if it can only be in 2 boxes. If you find one that's in 4 boxes, that's actually fine. That can be resolved. So you basically, you have within 2 rows and 2 columns, the digits line up like that. If they occupy 4 boxes, then that's completely resolvable. Yeah, those 5/8 there is a perfect example.
I was looking for the longest time. I couldn't find one. I should have marked one.
I guess I stalled for you. Because if you think about it, if those were 5/8 pairs, say the 8 in box 8, if that 8 were placed, the 8 in box 8, then that would give the 5, and then the rest of the unique rectangle would resolve. So it's resolvable externally, so it's not a unique rectangle.
Or to look at it another way, you can't just switch the 5 and the 8 in purple cells because there's already 8 there, and there's already a 5 there and an 8 there and a 5 there.
Yeah, exactly.
Now this is a deadly pattern, an unavoidable set. I didn't have that one in particular highlighted, but there is one there. It's a more complicated one.
Oh, okay.
You can switch all of the 5 and 8s in that pattern.
Oh, all 8 purples that you list.
Yeah,
okay.
All 8. Yeah. So anyway, so you have to be careful. For a simple 4-cell rectangle, it has to be in 2 boxes. Another way to look at it is if it's on 2 digits, you have to have both digits in every house that is part of that. So this didn't work because while I had the 5 and 8 in the rows and the columns, I didn't have the boxes.
Right.
But once
you
I
add the boxes.
add those, I still have the rows and the columns because these line up. And additionally, I have the boxes. So you can have more complicated patterns is the point here. You don't just have to have 4 cells. This is the most common that you'll see. It's the easiest to recognize as well when we get to uniqueness techniques.
So we'll go over later how to use these in uniqueness.
But there are more complicated patterns. So the green that I have highlighted here, this is a 6-cell pattern on 1 and 2. And like I mentioned, I have the 1 and the 2 in this row, this row, this row, and these columns, and in these 3 boxes. So if I were to switch all of the 1s and 2s in green, I would have a valid solution. So at least one of those has to be given for the puzzle to be unique. Here's another example that looks kind of like a unique rectangle, but then it's bent here. It makes this L shape. So that's another way you can have a 6-cell pattern. And then this is an 8-cell pattern. It's very similar to the 5-8 pattern.
Am I right to say that with a 2-value pattern like this, it's going to always be the same, like the number of rows, number of columns, and number of boxes occupied will be the same number?
Yes. Yeah, for 2 digits.
And it's going to be the number of cells divided by 2.
Yeah, I guess for any number of digits. That's probably not true. I think you can have patterns where, say you have a pattern on 1, 2, 3, but in one of the boxes it's just a 2, 3 pair. I think you can have things like that.
Okay.
Yeah, we're gonna get to an example, something like that.
Okay. But for 2 values, that's going to be true.
Yes, 2 values that'll be true. In fact, another thing you can say is that for any 2 digits in a Sudoku, there will always be at least one unavoidable set just on those 2 digits, because you can't leave both of those digits out of the Sudoku.
Yeah.
You don't have any way of telling them apart.
Yeah, if you only give 1 through 7, then the 8s and 9s are going to be
right.
swappable in the 18 cells they can occupy.
Exactly. So at the very least, you will have a big 18-cell unavoidable set for any pair of digits. So already we're talking about, 36 pairs of digits? So that's already 36 unavoidable sets. It'll be more than that on the 2-digit patterns because I have things like this. So my 5-1 pattern is 8 cells here. Here's another 4-cell pattern on 5 and 1. And here's another.
Yeah, they're all over the place.
Yeah. So 6 plus 4 plus 8, that's my 18 cells. But in this case, it's divided up into 3 separate groups. This is actually important for setting, not that you're using uniqueness techniques, but sometimes what will happen when you're setting a puzzle is won't have placed a 1 or a 5 anywhere, and it matters how these cycles are divided up. In this puzzle, I need 3 digits from 1 and 5 to cover each of these sets. But in some puzzles, I only need 1 because it's one big 18-cell pattern, and just having 1 digit will disambiguate both.
And so knowing this can save you a lot of frustration while setting. If you can recognize when you're setting that, oh, I've got these sets of blank cells that are going to end up being, this deadly pattern. Either I need to make sure they don't end up that deadly pattern, or I need to give something within that collection of cells.
Yeah, this comes up a lot, especially when you're trying to set a minimal Sudoku of whatever variant. I remember with setting White Root, for example, with the killer cages, a lot of times what will happen is you'll have some minimal-ish pattern of cages, but the way it works out, there's nothing to disambiguate these 4 cells, say. So you have to tweak things so that somehow we're getting information that's breaking this up.
Yeah. So either you're putting a killer cage in that area to disambiguate the 1-5s, or you're changing other things to end up with a solution grid that doesn't have those 1-5s in the solution.
Like maybe I'm putting a 3 cage here so that there's definitely not a 1 down here. Now that may result in another deadly pattern, but you gotta keep tweaking. Okay, so we talked about the essentially different solution grids. There's 5-point-something billion. So that was part 1, enumerating those. For each solution grid, this is what the group did. This was McGuire et al. And we're going to link this paper if you're interested in reading details. Because I can't go into all the details. I don't totally understand some of it, but I can give you broad strokes. So what they did is they enumerated the unavoidable sets for a given solution grid. So we're looking at this solution grid. We start finding these unavoidable sets, and there are a limited number of ways that they can appear in the grid. Obviously, your 4-cell pattern, you have to have 2 cells in each box. So you're checking things like this. Is that an unavoidable set? It's not. Is this an unavoidable set? Is this an unavoidable set? But they had some set list of patterns that they used. Typically, they would find around 360 per solution grid. As low as 200, as high as 500.
That's actually a lot lower than I thought it would be.
They were only going up to size 12, I believe. Okay. So there will be some that are larger, but that was enough. That's kind of the goal is not to generate all of them. The goal is to generate enough of them for the next part of the problem. So what they're trying to solve here is, I have the solution grid. I want to know if there are 16 givens that I can give that will give a solution. And I can't just do 81 choose 16, because that's a really big number. So I want to narrow it down. So the way they narrowed it down is they generated these unavoidable sets. And then they solved a version of what's called the hitting set problem. So what they're looking for is all of the ways to assign 16 givens so that there's at least one given in every unavoidable set that they have. There may be other unavoidable sets, but at least they're going to hit all the ones that they have. And if they get a 16-digit puzzle, then they can check if it has a solution. Just hitting all the unavoidable sets isn't going to guarantee that it's unique.
Right.
But it filters a lot of possibilities out.
Right.
So that's kind of how it worked. The hitting set problem is NP complete. NP hard, I think, even. Now, that doesn't necessarily mean you can't do it. I mean, the whole PNP is on asymptotic scales, so as the puzzle gets much, much bigger, it becomes much, much harder. So it doesn't say a whole lot about 9x9 Sudoku necessarily, but it's a hard enough problem that really the biggest part of the paper is novel ways to find these quickly. But that's what they did. They put together a program to find all of the possible 16 given hitting sets for their group of unavoidable sets, checked if any of them had a unique solution. Took about a year.
And so they had to do that for every
one of the 5.4 billion essentially different solutions.
So they actually have a list sitting somewhere of 5.8 billion classic Sudoku solutions.
Yeah, So this was originally generated. Ed Russell, Red Ed. He's had at least one puzzle featured on Cryptic Cryptic a while back. It was a X-Wing puzzle, actually. And I'm blanking on his name. Jarvis. Can't think of his first name right. Fraser Jarvis. I think that's right. Hopefully that's right. Anyway, they were the first ones to actually count for essentially different grids, and that's an interesting problem on its own. You use something called Burnside Dilemma to figure out the stuff to do with the equivalence classes and how many automorphisms there are. And things like that. So it's interesting stuff. They calculated that. That list has been generated before. I know Glenn Fowler had generated it at some point and used his compression algorithm on it. And it's still a pretty big file. But, yeah. So it's out there somewhere. It's probably hard to pass around. So I would recommend trying to find it so you can look through all 5 billion solutions. But it's there. So that's what they'd use. So just as a practical example for this, because this is all high level theoretical how they did it, and it took a year of computing time to actually prove it. Let's go back to the most canonical grid. We're actually going to prove that this grid doesn't even have any 17 given puzzles. So not only 16, it doesn't have any 17s. And the way we're going to prove that, all of these unavoidable sets that we looked at, we need 1 given.
Right.
But there are some unavoidable sets that you need 2 givens. For example, here's one right here. If I leave all of those cells empty, back over here, if I just have that, obviously that's going to have multiple solutions.
Yep.
But even if I put a 1 here, that is not enough to disambiguate it. There's still multiple ways to do it. You can have the ones here, you can have the ones here, and you still need to disambiguate 2 and 3.
Yeah, so you can kind of think about it as like it's a 3 factorial number of solutions. And so dividing that by 2, you still have, is that right? You're dividing it by 3 by placing that 1. You still have 2 solutions remaining.
Yeah. Or another way to look at it, it's effectively a 3x3 Sudoku, 3x3 Latin square.
True. Yeah.
And you need to give at least 1 of 2 of the digits,
right,
to resolve it. So
the 2 and the 3 can always
be swapped. If I put a 2 there, now we can solve it.
Yeah.
This sort of thing. It's solved. So that's one possible solution. Okay. So I need 2 digits in those red cells.
Yeah. So this puzzle has a lot of 3x3 mini Sudokus in it.
Yeah, and that's kind of the point.
Yeah.
We can divide the entire grid. I'll just do this stack, but the same applies to the other 2 stacks. So there are actually 9 disjoint 9-cell unavoidable patterns of order 2, meaning they need 2 digits. So if we have 9 of those and we need 2 digits in each, we need at least 18 digits to have a solution. There are some solutions, or there are some puzzles with 18 for this grid. Most of them, if you just randomly picked 2 digits in each of the sets, you're not going to end up with a unique solution. Well,
of course, I could give 18 givens easily and have it not be unique by just not hitting all the sets, right?
The key thing with this one is because of the way it's divided up. By placing 2 givens in red, say, if I place the 1 here and the 3 here, I guarantee I'm disambiguating red.
Right.
If the rest of the puzzle is filled in.
Right.
And if I put 2 digits in yellow, I'm guaranteeing that I'm disambiguating yellow if the rest of the puzzle is filled. So if I pick 18 givens, 2 for each, and make sure that they're 2 that will resolve the little 3x3 Sudoku, I still have to worry about, well, placing the 4 here and the 6 here, that doesn't rule out this being a 7, say. Unless I've also placed a 7 here, or, whatever. So just because I have the unavoidable sets covered doesn't mean everything's fixed.
Right. So just because we've resolved each of those individual 18 unavoidable sets does not mean that we have a unique solution, but it's a requirement for a minimum number of givens.
Right. Yeah. So that's the very, very simple light proof that you need 18 for the most canonical. There are some grids that require 20 givens. There are not any that require 21. That may be a conjecture. I'm not totally sure. I don't remember if that's been proved. But most grids will have an 18. There are very few 17 given Sudokus. So in generating the 17 given Sudokus, most of these were actually generated just by people finding them and then doing neighborhood searches, adding digits, removing digits. But actually verifying that we have a complete list involves looking at each solution grid, looking at different patterns of placing digits within the bands, and unavoidable sets and things like this. There's a very clever program that I know very little about, but I've recently gotten involved in spending some of my computer time running this, looking for 17s. And a few of us are enumerating all of the possible 17 Sudokus. Currently, there are 49,158 that are known. And I think the last 7 of them were found in the last 15 years, something like that. We're not finding many more, is the point.
So you're finding one every other year, basically.
Yeah. But yeah, so I very recently started searching. I have found 30 in the band that I'm searching. All of them are already known, as expected. I think there's a total of 49 band that I'm looking at. But we go through all the bands and we prove conclusively whether we found them all or not. And maybe we'll find a new one, who knows. But that search is getting close to being complete. I can't say percentage-wise exactly how close it is, because the part I'm involved in, there was a lot of other work done even before the current search. So anyway, before too long, we'll know exactly how many there are.
What's interesting is most of those 17 given puzzles are actually very easy to solve.
Yeah, like 80-something% are basically.
Yeah,
I believe.
So a lot of them are just singles.
Yeah.
And so that's actually something that comes up, at least in my neighborhood of Sudoku theory, where people, new people come in and they want to evaluate the difficulty of puzzles, and their first thought is by just counting the number of givens. And that is a terrible way to evaluate the difficulty of a Sudoku puzzle, because the number of givens does not correlate at all with the difficulty of the puzzle in any way that we've been able to determine.
Well, I mean, if you have 58 givens, on average, you're going to have a very easy puzzle.
Sure, but like you said,
there are puzzles with 58 givens that are harder than some 17 givens.
Yeah.
And I've been involved for a while searching for hard puzzles. The hardest puzzles known, at least by the Sudoku explainer metric, are 21, 22, or 23 puzzles. But there's kind of a spread. 19 clue puzzles. The highest known is 10.5, and then it jumps up to 11.8 for 20 clues, and it stays at 11.8 or 11.9 or 11.7 up to 30 clues before it starts tailing off again. So it's a big range of clues, clue counts for the hardest puzzles. For higher clue counts, it's hard to find a puzzle that is minimal that you can't remove given. That's usually what we care about with the hard puzzles, is finding minimal puzzles.
Right.
Because once you have a puzzle, you can do singles on it, and you still have just as hard a puzzle. Just the singles are.
Yeah.
But high clue count puzzles that are also minimal are pretty rare. Highest known is 40. I think there's 2 of those. So these are all topics that we could probably spend a whole other hour on.
That's fair.
But we'll move on to some uniqueness techniques now.
Okay.
So the thing to be careful with uniqueness techniques, so all the other techniques that we've covered in the series, when you use them, they are proving something about the Sudoku. When we use an autogon, we are proving that one of these digits has to be a guardian, or we have a broken pattern. We have no solution.
We have 0 solutions. Yeah.
What uniqueness techniques are saying is, if there is a unique solution, then something. So we're going to start with very basic unique rectangle. So this will look similar to our 3-4 over here. But we have one extra candidate. So we're solving this puzzle. I'm just doing pencil marks today rather than doing a full puzzle. We're solving this puzzle, and we've come to the conclusion that there's a 1-2 pair in this box, and there's a 1-2 pair in this column, and this cell is limited to 1, 2, 3. What do we know about this Sudoku? What we know is that if this digit is not a 3, say it's a 2, then that's forced, right?
Yep.
And that would be one solution. Or a whole class of solutions for the puzzle. But it could also be a 1, and that would be a solution. So what I'm saying then is, if this cell is not a 3, I have at least 2 solutions. In fact, I have an even number of solutions, however there are. Or I have 0 solutions. It could still be unsolved without it.
Yeah.
And in fact, that's going to be the case. If it's valid, use it. So what I'm saying is, if there's a unique solution, this is a 3. And therefore, if it's a unique solution, the 1-2 deadly pattern has 0 solutions. It's broken.
Yeah.
So that's the basic deduction that you can make with it. If there's one cell that is not part of the deadly pattern, the 1-2 pattern, then it has to be that other. You could have more than one candidate. You could have like a 1, 2, 3, 4 here, and then you're saying this has to be 3 or same concept. But again, this only applies if you know that the solution is unique. If you don't know that it's unique, say you're solving this from some publication that you don't trust, I will not name any names. I don't really know any names. I don't really solve puzzles outside of the community of people that I trust to make puzzles. But there are publications out there that will publish Sudoku puzzles that have more than one solution. If I don't know that it's unique, I can still try and fill in a 3 here, and I might find a solution. But I might not. It may be that there are exactly 2 solutions, and they correspond to that deadly pattern of 2. You just don't know. So you can only use this if you trust the source.
Yeah, and so Sudoku rules that they are generally listed as don't repeat, in a row, column, or box. So there's basically 3 rules, right? Digits don't repeat in a row, digits don't repeat in column, digits don't repeat in a box, and you're placing the digits 1 through 9. There's no rule that there's only one solution to what they've presented to you. And there's sort of just an unwritten rule that by convention, there will only be one solution. And the reason for that is there is no logical way to solve and get a single solution if there is more than one solution.
Right. Yeah, it's sort of an unwritten, this is a logic puzzle, so there better be a logical path. Yeah, so we generally frown on using uniqueness. That said, uniqueness techniques can be really interesting, and there are definitely puzzles out there that are very hard if you don't use uniqueness. I have an example. I know Shai and Jovial have been working on other uniqueness techniques recently, among others. I'm sure there are other people doing it. Sometimes that is the best way forward to solve the puzzle in a reasonable amount of time. But my personal feeling is, unless you go into the puzzle knowing that uniqueness is what you're going to need, and the guarantee that it has a unique solution, then it's a little sketchy to require it.
Yeah, and I think context matters because if you know the Sudoku you're solving was handcrafted, a human sat there and said it, it's unlikely that the human used uniqueness in their setting, because you can't use uniqueness while you're setting.
Right.
And so there are humans who have created puzzles that they intend uniqueness to be used, but those are very few and far between, and they're intentionally, someone has sat down to be like, I want to show off uniqueness, and that those exist. But usually there's something in the description of it or the rules or something that'll say something along the lines of, a computer has verified this has a unique solution.
Yeah.
Right.
Yeah, I know Simon solved one on Cracking the Cryptic a while back that it was sent saying, this shows off all these uniqueness techniques. And Simon ordinarily would never use uniqueness, but in that case, he was showing off the intended path, which was uniqueness. But
I would say that the other context here would be if you're playing computer-generated puzzles. And often the way computer-generated puzzles work is they use some sort of brute force method to get a unique grid, and then they score the grid with a difficulty, and then they determine based on the difficulty whether to present that to you or not, based on what you decided you want to solve. And when they score it for difficulty, the computer may have uniqueness techniques built in, and the only reason it got the difficulty it did is because uniqueness was considered an easy technique to use. Yeah. So in those contexts, uniqueness, I suppose, would be fine, because you know that the computer generating your puzzles is assuming that you're going to use uniqueness to solve it.
Yeah, the third context that I would mention, and Mark from Cracking Cryptic brings this up, is competition solving. In a competition setting where you're just trying to solve it as fast as possible, and you have a high degree of confidence that there's a unique solution, if you spot a unique rectangle like this, you're going to use it.
Yeah.
And then if it breaks, then you know that something went wrong with the competition puzzles. Probably, but it can definitely be a shortcut. So you'll see that. So I have a few more examples for deductions that you can make.
Okay.
These are mostly based around the unique rectangle. There's one that's not. There's a wide variety of things you can do with this, including chains and loops and all sorts of crazy things. There's the whole topic of Girth's symmetrical placement, which is just a completely different uniqueness argument. I'm not going to cover that today. If there's a lot of interest on uniqueness, like I said, I know certain people are working on uniqueness puzzles for a pack. I don't have any idea when that pack is coming out, but maybe it'll get revisited at some point down the line. But yeah, so I'm just going to go through a few more of these.
Okay.
same unique rectangle here. I'll ask you what you think the deduction is.
Well, I think that row 4, column 9 can't be a 3, or it creates a unique rectangle.
Exactly. So if this were a 3, then neither of these could be a 3 and be left with a 1, 2 deadly pattern. Right. Another way of looking at it is one of these has to be a 3, so there's a pointing pair.
Yep.
3 to eliminate it. So this has to be a 4.
Yep.
Okay. These actually have names. They're uniqueness type 1, 2, 3, 4, 5, 6.
Okay. Are these in order or?
I think so. Okay. I looked them up on a random website what the types were.
Okay.
I've never paid any attention.
Yeah, I don't pay attention to the types. As long as you understand the logic, it doesn't matter what the name is.
I'm pretty sure there's a type 7, if not a type 8. That was too much. So
yeah.
All right, this one's a little more complicated. You want to have a stab at it?
Well, there's a strong link between the 3 and the 4. And so is that used in some way? The 3 or the 4 must be true. But I don't immediately see what that's used for.
So like you said, there's a strong link between the 3 and the 4. One of them must be true, and one of them must be in the cell.
I
so
see.
That accounts for the 3 and the 4.
It's a 3-4 pair. Got it. Yeah.
So you can put a 5 and 6 there. So yeah, this is kind of almost an like set version of this, or a strong link sort of loop sort of thing. And
actually, if you think about it, if those 1s were removed or the 2s were removed, you'd have just a triple.
Yeah. I can't remove them because they're from puzzles, but anyway.
I think you can these, actually.
Really?
Yeah.
You can. Cool. Yeah. So if those weren't 1, then you have a triple. And if those weren't 2, then you have a triple. And we know they can't both be 1 and 2, so yeah.
Yep.
But yeah, however you want to see that. This one.
Well, so we know 1 is going to be in that unique rect, so 2 can't.
Yep. So 1 is forced into one of these 2 cells. It's a pointing pair, claiming sort of thing.
Yeah.
Since the 1 is there, we know one of the other cells has to be the 3 or 4. Doesn't. This one will actually come up quite a bit with exosets, oddly. If I'm looking at an exoset and YZF, which supports it, it will have uniqueness deductions from exosets because sometimes you'll end up with this sort of pointing pair result from the exoset, and then you can combine it. This is very similar to type 2.
Yeah, so one of those 3s has to be true. And they all see that 3-4.
Yeah. Yeah. So this is kind of a sort of a pointing triple, but a pointing bent triple. They don't all see each other, but one of them has to be true. It could be both of these or 3.
Right.
We don't know, but if this were 3, it would eliminate all the things.
Right.
So like with the Autogons, we had guardians. These are kind of like guardians. I don't think they're called guardians because it's uniqueness instead of Autogons. One of those has to be 3, and I'll see that. So
I would call them guardians, but there's a reason.
This one's a little trickier. It's not that much trickier. But.
Well, so I can see that you're forcing 2 to appear twice in that unique rect.
Yep.
And so 1 can't repeat twice, but maybe there's some deduction I'm missing. That's obvious.
True. That's true. 2 has to appear twice. This is basically fake X.
Yeah.
If it appeared in those 2 cells, it would build them both guardians.
Oh, I see.
Can't do.
Gotcha. So the 2 has to appear twice, therefore it appears twice.
Yeah. Now, additionally, either this is a 4 or this is a 3. But we actually can't make any eliminations on that basis.
Can't you place the 2s, though?
Yeah, you can place the 2s. You can't make any eliminations on this basis. You just know that these aren't both 1. So you have a strong link between the 3 and the 4. But you can't determine which is which.
So you could do some sort of AIC that used that strong link. Yeah. It's like a uniqueness strong link. That's
right.
Interesting.
Yeah. You can have strong links out of uniqueness, and it's, if you consider uniqueness valid, it's a valid strong link, and you can use it in any other context where you would strong. But yeah, I think this one is the most interesting, just because we're saying 2 has to be here twice, and therefore 1 only appears once. But we're not really making any eliminations based on 1. I mean, we're placing the 2s, so that's eliminated that way. But it feels different to me.
Yeah, it's an interesting one. It almost it feels really strange because, like, you sort of think in your head, well, I can just place those 2 1s now. Like, they're not they're not unresolved, so. Right? But they are resolved because. The uniqueness argument. You could swap the 1 and 2 in the final solution. Yeah. So that must not be how it ended up.
Yeah. So if you came across something like this and you were wanting to use uniqueness, you would probably want to mark these cells, because once you've placed the 2s, it's no longer obvious that this is a deadly pattern. Yeah. So you've placed some digits. But you have to keep in mind, no, those can't both be 1s because I placed these 2s based on uniqueness.
Yeah.
So. Anyway, all right, last one. This is just a little bit of a complication. This is called an extended rectangle. One example of an extended.
I see. So is this like 2 overlapping unique rects, basically?
It's basically a size 6 unavoidable set.
Okay.
So if that's not a 4, then I could have 2, 1, 3. And 1, 3, 2. Or I could have 1, 3, 2 and 2, 1, 3. There's nothing disambiguous. So it's just a bigger unavoidable set.
So if you undo one more time, that 4 is placed then.
So that 4 is placed. You can also see it with something like this, I think, where you have 2 cells in each box. Maybe you have a 1, 2 pair here, 2, 3 here, 1, 3 here.
So the point is that, at least, so in the first example that you have there, it's 3 pairs. Yeah. So what is the criteria to identify this, I guess is what I'm asking. Like, what works and what doesn't?
Yeah, so in this case, it's 3 pairs in the columns. And the 3 digits form a triple in the boxes.
Is this limited to 2 boxes? I think it is, right?
I mean, you could have a bigger version of it, like these.
Yeah.
But in that case, you would have 2. Like, it would be an unavoidable set for 2. Mm-hmm. So you would need 2 guardians to be true. And it's probably just really difficult to set something like that up. Honestly, in a puzzle. I don't know. I haven't tried. Maybe.
I guess what I'm asking is if that 2-3 pair were in column 4 instead of column 3.
Oh, if it were over here?
Yeah.
I don't think it works in that case.
Right, because the box.
Because of the box. Yeah.
Yeah.
So if I determine this as a 2 based on this box, that disintegrates the whole thing.
Right.
So yeah. For this particular pattern, the columns all have to be in the same stack.
Okay, but then this example you gave here is a little bit. It actually spans 3 boxes.
It spans 3 boxes, but again, all of the columns are in the same stack.
Mm. Okay.
So yeah, it's kind of the same concept. Just one of each of them is offset. So in this case, I can have the 1, 2, 3 like this, or I can have the 1, 2, 3 like this, and then fill in the others. But there's nothing to disambiguate. So I would need some guardian to be true. in that case. And it could look like this,
Yep.
even. And now I have a pointing pair of 4s. But yeah, that was my last example. Like I said, there's a ton of things you can do with this. As we saw, some of these examples will give strong links between the guardians, or whatever you want to call them, whatever's preventing the deadly pattern. So you can use that in a chain, but even use it in a X-wing in theory. I don't see why not. Although it wouldn't be a full X-wing because of the spanning boxes thing. But yeah, so it can get much more complicated. I just wanted to give a few examples that relate to the unavoidable sets in the paper. So
yeah,
that's what I have.
Something you didn't bring up that I see used a lot, actually, especially near the end of puzzles. I frequent the Sudoku Reddit, which is mostly a lot of. There's some advanced discussion there every once in a while, but it's a lot of people just posting puzzles asking for help. And very frequently, I see suggested to use bug +1, which is very much a uniqueness argument, or a uniqueness. What do you want to call that? Uniqueness strategy, which is valid if your puzzle's unique. I always try to give an alternate way to get through it if someone has suggested bug +1, just in case someone doesn't want to use uniqueness. But like it's usually either a Y-wing or a skyscraper or something along those lines that finishes you off.
Pretty much guaranteed to be a Y-wing or a skyscraper or something along those lines. I don't think it can get too much more complicated. Just to give you an idea of what a bug is, this is a terrible example. It wouldn't actually appear in a puzzle, but this is a bug,
which stands for by value universal grave.
Yeah. So what the by value part means, we talk about by value in cells. So there are two possibilities for the cell, 1 or 2. So it's a by value cell. The by value part of by value universal grave is actually more general. It's including by local. So you have a bug if for every undecided cell and for every undecided digit in a house, there are 2 options. So this cell, there are 2 options. This cell, there are 2 options. In this column, there are 2 places that 1 can be. There are 2 places that 2. In this box, there are 2 places 1 can be. And if that's true for everything in the puzzle, you have a bug, which means you have a deadly pattern, and at least 2. Well, exactly.
I think it's exactly 2 solutions.
Exactly 2 solutions in that case. Maybe not. Because I think technically this would be... I guess they're...
They were in your... Yeah.
Yeah. I think technically that would be a bug, and it would be sort of disjoint parts of the bug.
But if you have a fully connected bug...
If it's fully connected, then you have 2 solutions. You have some power of 2 solutions, I think. Yeah. It may just be a multiple, but I'm not totally sure off the top of my head.
I think power of 2 sounds right too.
Yeah. So bug +1 is where you have that, except you have 1 extra candidate somewhere.
It doesn't even have to be a new candidate. It just has to be. In this case, the 2 appears 3 times in that cell and 3 times in the column. So you've now identified that must be a 2 in order to not have bug. Yeah.
Now this particular example is a terrible example because I've kind of established that this is the only place for 2 in the box. Yeah. But you'll end up with something like this, where every cell has 2 possibilities, and every row has 2 possibilities for a digit, except for 1. And that's your +1. So that's a 2.
All right. Well, yeah, we don't have any examples of bug that we can show you at the moment, but I'm sure you'll encounter it in your own solving at some point, or you can look that up yourself. But if we do cover uniqueness again, maybe we'll cover bug and girth and stuff like that. But we don't plan the next episode to be, this isn't a uniqueness series. This is a one-off. We wanted to cover this because I think it's really interesting how uniqueness was used in the proof that you can't have 16 givens to create a unique solution, as well as the hunt for 17 givens, the list of that. So it's useful in the theory of Sudoku It's also useful when setting. It's useful in solving in the situations we described, such as competition, or if you know that you trust the publication of it. And, again, Sudoku is a single player game, so solve however you'd like. We generally try to avoid using uniqueness, but it is certainly a valid strategy in a lot of situations. Just be careful, because if your puzzle is not a good puzzle, then it might have multiple solutions, and then you're gonna run yourself into a wall. So
yeah, channels like David's, he's trying to present a logical path for the Sudokus he solved, so he's gonna avoid uniqueness. He might point it out when he sees it, and say, "Hey, this is where you could use uniqueness," but he's trying to present the logical path for you, and this is not part of the logical path unless you know it has a solution. And you generally don't want to use that if it's not stated up front.
Yeah. Also, I deal in variants a lot. I solve a lot of Sudoku variants. I don't solve very many classics on my stream or in my videos, and so I don't trust that a certain variant is going to preserve classic Sudoku uniqueness techniques. Like, as soon as you introduce something like anti-knight, like, it's completely out the window, because you can have just a 3 placed, in box 6, and then that sees into box 5, and now this uniqueness pattern gets resolved by that. But there's a lot more subtle ways that uniqueness can break, in ways that may not be obvious, and so I avoid it whenever I solve any variant Sudokus.
Well, and in fact, when people are setting variants, uniqueness is used way more often in terms of placing that final constraint to make the puzzle unique. So you'll often see this would be a deadly pattern, except for that black dot that you put there.
Yeah.
So that'll come up a lot, but you have to be really sure that the uniqueness argument applies when you deal with variants.
Exactly. All right. Well, I hope everyone enjoyed this episode. We're both glad to be back and making more Sudoku discussion episodes. And we don't have any challenge puzzles for you or anything this time, so you have a break from that. But hopefully you enjoyed the episode, and be sure to like and subscribe if you have not. I do have a Patreon. If you'd like to join that and support me on a monthly basis, that supports all of my efforts in Sudoku land, the Sudokult discussion videos, with the other videos on my channel, my bi-weekly streams, and the solver work that I do, and all that stuff. If you want to support me on a monthly basis, you can join Patreon. We also have a Discord server that I share with Bremster,Zetamath, and Scott Strossall. And we sort of co-share that server, so you can check the description for a link to join that Discord and hang out with us and talk about Sudoku and talk about the videos and anything else. So all that said, hope you enjoyed, and we'll see you next time.